Welcome back to our discussions of introduction to machine learning, and we are going to pick it up from where we stopped last time, where we are finding the values of beta, or the model parameters, which will give us the minimized cost function. So we last looked at obtaining beta 1, and remember, if I can remind you, all of whatever we have done so far is in regard to simple linear regression. So we will see for multiple regression, linear regression, but as of now we've been covering for simple linear regression. Allow me, we pick it up from there and we continue our discussion. Right, so let me get a new page for this case. So we are going to see that in action. Now we are going to do an example and we see how it happens. Right? Okay. So we're going to do an example. Now we're going to see, given age, which you try independent variable, given age, can you predict weight, someone's weight, which is a dependent variable for this case. So given age, now for this case our age is in first one, aged 1, 2, 3, 4, and then weight, let us stop there. Weight, we have 2, we have 4, we have 6, we have 8. So given age, can you predict someone's weight? Right, first we're going to assert that there is a linear relationship between age and weight, and we make our hypothesis of that there is a linear relationship between age and weight is equal to beta naught plus beta 1 x. Right? Okay, this is the relationship we are asserting. Right? This is the relationship we are asserting. This is our hypothesis. Now, meaning we need to predict this. Which is y predicted value to be 1. Okay. For this case, allow me initiate the beta naught to be equal to 0. This is just an arbitrary value. Beta naught to be equal to 0 and beta 1 be equal to 1. These are just arbitrary values. I'm just getting arbitrary values so that we can start. So I'm saying let beta 1 be equal to 0 and beta naught to be equal to 1. So when I feed them into our model here, then I can be able to start the prediction. So meaning my model will be equal to, because this is 0, so this is 0 and this is 1, so I remain with x. My model will be equal to x. In other words, the predicted value, this is what our model will predict. This will be 1, this will be 2, this will be 3, and this will be 4. Right? So I need now, okay, I've now made the prediction. Now I need to start asking my model, how is it performing, by finding the cost function. By finding the cost function of the model. By finding the cost function, we know the cost function is equal to 1 out of 2m to n summation of I is equal to 1 up to n into the predicted value minus the true value squared. That is my cost function. So I need to find this into our model. Right? So let me make that column here, the predicted value minus the true value. right? So predicted value minus the true value column, it will be the predicted value is 1 minus the true value, which is 2, so it will be a negative 1, right? And this is 2 minus, this will be a negative 2, this will be a negative 3, and this will be a negative 4. So the summation will be 10, negative 10, right? The summation will be negative 10. The summation will be negative 10. Maybe if we take the square of that, which is the predicted value minus the true value squared. So this will be 1, this will be 4, right? This will be 9, and this will be 16, right? And the summation will be 30, right? The summation of this will be 30. So this one, the whole of this is 30 now. So meaning my cost function will be equal to 30, which is this, as we have seen up there, over n. Our n is equal to the number of rows for this case, which is 4, the number of the data set, which is 4, right? So 4 times 2, which is 8, and is equal to, so 30 divided by 8, isn't it? Is it 7.5? 30 divided by 8. Yeah, 3. It is 3 point 2. 3 point. Oh, sorry. What answer did I got in? It is 3.75. 3.75. So that is the cost function we have, right? Now we need to minimize that cost function by finding the new values of beta, right? So we need to minimize that cost function, that value, by finding the new number of beta. And from our last discussion, we saw that finding a new value of beta, let me say beta I, is equal to the previous value of beta, which is beta I minus 1, then minus beta I minus 1, then minus the learning rate, then times the partial derivative of the cost function, with respect to the respective beta value, right? With respect to respective beta value, let me say beta I. So that was the formula, and we saw we did this for instance for beta 1, for beta naught, the value of beta naught will be equal to the previous value of beta naught, minus the learning rate and the partial derivative of the cost function, with respect to beta naught, and we saw this. We calculated how we obtain this, right? So beta naught, the current value of beta naught in our value, will be equal to the previous value, which is the previous value of beta naught minus the learning rate, into 1 out of n summation of I is equal to 1 up to n into the predicted value minus the true value. This is what we saw earlier in our discussion right? So that's what we're going to do now. We're going to find the real value. So the current value of beta naught will be equal to, and we discussed the instance of the partial derivative of the cost function, that it shows us the direction in which the beta value should be, or the beta should take, in order to reduce the cost function. And we said if the value of the cost function, if the value of the partial derivative of the cost function, this one, the whole of the bracket, if the value of the partial derivative, of the cost function, this one, the whole of this, if the value is positive, that literally indicates that we should reduce the beta value in order for us to obtain the minimum cost function. And if the value is negative, then it tells us that actually the beta value should be positive or should increase in order for us to minimize the cost function. And we're going to see that in play. So we're going to this you're going to now, okay, let us obtain now the value. The previous value of beta was 0, right? 0, then minus learning rate. So let the learning rate alpha be equal to 0.01. We're going to use the learning rate of 0.01. So to be 0 minus 0.01 into the summation of this, from our table. Did we find that? Yeah, this is, which is negative 10. The summation of all of that is a negative 10. The summation of all of this is negative 10. Negative 10 out of 4, right? N is 4. Negative 10 out of 4. So now, meaning, as you see, this is what I've just illustrated, that the value of the partial derivative is now negative. Literally, it says that the value of beta naught now should increase in order for us to reduce the cost function. That's what it says, and we're going to see that if it is true. But as of now, it says that since it is a negative, this one is going to, the bracket is going to give us a negative answer, right? So which is 10 divided by 4, it is negative 2.5, right? And negative, it now says for us to be in a position to reduce the error we got, we needed to increase the value of beta. So 2.4, negative 2.4 times 0.01, negative 0.1 to be a positive. So beta, now beta, the beta value, the beta naught value is equal to 0.025. Now the beta value is 0.25, and I think it has increased from 0, right? It has increased from 0. So then we need to find the one for beta 1. We need to find the one for beta 1. We need to find the one for beta 1 and see. Need to find the one for beta 1. Need to find the one for beta 1, and we see the beta 1 value. So still we are going to follow this one. So we're going to follow this. But remember, actually this is where we picked our discussion from, of getting the value of beta 1, because that's what we ended our previous discussion with. So beta 1 value will be equal to beta 1 value will be equal to the previous value of beta 1, the previous value of beta 1 minus, remember this is where we stopped our last discussion, minus the running rate into the running rate into 1 out of n summation of I is equal to 1 up to n, and then the predicted value minus the true value, right? True value, then x. This is what we did last in the last discussion. That is what we obtained, right? So meaning we need to find this in our table to make everything simple, right? We need to find that in our table here to make everything simple, which is the predicted value minus the true value, then times x, right? Times x, to make our life so simple. So simple. So the predicted value minus, so this is I think this is then times x, which is 1. So this will remain negative 1. This will be negative 4. This will be negative 9. That is will be negative 9, and this will be negative 16, right? This 16, and this will give us the summation. It will give us a negative 30, right? Negative 30. So the summation for that is a negative 30 for this. So now we know very well. So the new value of beta 1 will be equal to the previous value, which was 1, then minus the running rate, which is 0.01, into this is negative 30, right? Negative 30 over 4, right? Because n is equal to 4, isn't it? Okay, so 30 divided by 4 is equal to 7.5, negative 7.5. And now this also tells us that, you see, because here the partial derivative, which is in the bracket now, is a negative, is going to be a negative answer, or is a negative answer. So it tells us that we need also to increase the value of beta 1 in order for us to obtain the minimum cost function, or in order for us to reduce the error. So that's what is going to happen. We need to increase the value of beta 1. So times 0 times 0.01 plus 1. So the new value of beta 1, is going to be equal to 1.075. You see, the value has increased 75. Now meaning our new hypothesis or model, our new model will be equal to, we saw the value of beta naught. The value of beta 1 naught is 0.025 plus 1.075 x, 75x. So this is our new model, right? Now we're going to make another prediction and see. So going to make another prediction and see whether the value will improve, the model prediction will improve. Now this is, so we start feeding in the values of x, and we see. So that when x is equal to 1, then plus 0.025 now, right? we are going to feed into this model, right? And we see, so this will be, now for the first value, it will be the first value. Let me say this is our second prediction. Second prediction. So this will be 1.1. This will be 1.1. Now when x is equal to 2, so 1. Okay, let me write our new values of beta 1 and beta naught here to make life easy. Is equal to 0.025, and beta 1 is equal to 1.075. I hope I'm right. That's what we saw down here, right? Yeah. Okay, so we make predictions now, and we see now when x is equal to 2, 1.075 times 2, then plus 0.025, then is equal to, so this will be 2.175. Okay, let me just write it. This is going to be 2.175. Maybe if I can extend it a bit here. If I can extend it a bit here, 2.175. Right, and the first one was 1.1. The first one was 1.1. Okay, so when x is equal to 3 times the 1.075, then plus 0.025 to be, so this will be 3.25, and then this will be 1.075 times 3, almost 4 plus 0.025. So this will be 4.325. So you see that even from here, you see that our model is going on improving slowly, tending to, it is increasing the predictions because of the running rate we took, which was of the running rate we took of 0.01, which is kind of slow. If you had took maybe 0.1, it would be fast. You would have seen that actually this is increasing so fast, the values. But let us go with the one we took of 0.01, and we see does the cost function reduce, right? So this is the new predicted value now. So we need to find a new error. So I think we should get another table. Let me should I insert another table up here so that we make okay, let me put it down. So we're going to, now we have the predicted values, the true value. Okay, let me just take the necessary values now for this case, which will be the necessary value. We need this and this, right? Then we get the rest. So we'll take the weight, so this is going to be the weight, this is b weight, and then the predicted value for this case, y, predicted value for this case, the one we have just predicted, right, y. So this is going to be, this is 2, if I can remember, this is 2, this is 4, this is 8, right? No, this is 6, and this is 8, isn't it? This is so this is 1.2, 1.1, here I have 1.1, this is, let me see, 2.175, 2.175, then 2.75, 3.25, 3.25, and the last three is 4.325, 4.325. So okay, that is now what we have, the true value and the predicted value. So we need to find the error, which is the predicted value minus, we need to find this, we need to find, and we see whether the error is reduced. Okay, we need to find this as well, where this is squared. I think this is what will help us find the error more, right? So now let's start with this. So 2 minus 1.1, which will be 0.9, but a negative, right? Because we are doing this minus this. So this will be a negative 0.9, negative 0.9, then 2.175 minus 4 to be a negative, this will be a negative 1.825, and then 3.25 minus 6, right? It is a negative 2.75, right? And this is 4.325 minus 8 to be a negative 3.675, right? So the square values of those squared value for this, it will be positive 13, right? 13 point, I'm going to 505.625. I would have rounded up to 4 decimal point, but let me take it the way it is because we want to minimize the error. Okay, so 3 point, let me just confirm that, 7, 5 times 3.675 Okay, then 2.27 squared, right? So this will be 5. This will be 5.1529, and this will be 1.825. This will be 3.0625. I would have taken a square root. I would have rounded off to 4 decimal points, but I want to capture the entire thing so that I see what happens to the error. So this will be 0.81, right? 9 squared. So now we find the summation for both of these. Their summations to be, I think let us start with the positive one, 13.505625 plus 5.1529 plus 3.330625 plus 0.81. So the summation here it will be 22 point. Okay, let me just use, let me type to minimize the space. It will be 22.79915, right? And the summation here to be 3.675 plus 2.27 plus 1.825 plus 0.9. So the summation here to be negative 8.67. So we have gotten that, and we know our cost function, and we know, so now we find the cost function. Our cost function will be equal to 1 out of 2n summation of I is equal to 1 up to n of the predicted value y at minus the true value squared, right? So, but we know this, we have calculated this actually, which is this, the last column, which is 2.799 2.79915 over 8, right? Over 8, isn't it? Over 8, and we see, so you can get me the value, anyone faster, you can get me the value 2.749915 divided by 8. So you see the cost function is now 2.8499 if I can take 4 decimal places, but you can continue the entire value, and you see that it is reducing. Remember the previous value we got, let me see the previous value. The previous value we got, the previous value of the cost function. The cost function, it was 3.75. Now this one, it is 2 point, so it is reducing. So what happens? We actually do the same thing. If we still want to reduce up to when we obtain the minimum cost function, we do the same process. We come back, we get a new value of beta, right? Using the formula, these formulas, the one we have used, these ones, you still get a new values of beta. You get a new model, you predict, you find a new cost function, then until when the cost function is approximately bearable, or I would say approximately to 0. I think if you get it in 0.00 something, it is the better. So we do that. But since we are human, that is really hard, because you may spend years doing that. So what we usually do, we write a program which takes those processes, until when we obtain a minimum cost function. And that is the bit of programming now. So we are going to implement that with the program, because we have realized as human beings, we don't have resources to take all of those processes till we obtain the minimum cost function, right? So with that example, allow me seal off the simple linear regression, right? And we are going now to start for multiple, in other words, for multiple linear regression, whereby if you have a function like this, where there are so many other betas, right, beta naught or any other plus, let me say beta 1 x1, then plus beta 2 x2 plus n. So where there are so many other independent variables to use in the model to predict the dependent variables. That's what we call multiple linear regression. We are going to see the case for multiple linear regression, and we'll pick it up from that point. I hope you have appreciated this, and now you really understand what happens in the background for these predictive models frameworks, right? As we will see them, So that's what happens for simple linear regression. We have really seen in details what happens, and what we are going to do after covering all of this, we will now start implementing them, right? So we'll write a program. For those who know now the program, who knows programming, they can actually start picking up from there. This is a very crucial point, this one for beta 1, because this is what we write a program which does this, right? And for the beta 0, this, and then for the cost function, and things will be very, very, very fun, right? It is very important. We will code this with our Python. We are going to use Python to code this and to ensure we build our own model from scratch, right? We have just understood what happens, and then we just need now, because we can actually go on and on, but we are human. We can't do this more than 100. You may see that it may take even 1,000,000 times, right? Obtaining the minimum cost function. We don't have that resources, and we don't have that energy to do that. So that's the essence of us writing a program or a script, but it is a program which does that for us. So, but before that, we are going to first look at the case for multiple linear regression. What we have covered has been for simple linear regression. So allow me to pick up our next discussion from there for multiple linear regression, right? This, and we'll also enjoy it, and then we switch to programming those processes. Thank you.